So after that, we have the x1, y1, and z1 coordinate systems. So as you can see here, we have the x1, y1, z1. So which indicates that the omega has been rotated. And right now, we are going to rotate the phi. So as you can see, the phi is along the y-axis. So it will be like this. All right, it will be like this. So the y coordinate doesn't change. And what changes is the x coordinates and also z coordinates, because we will change it like this. Okay. So in this case, we can also simplify it. It becomes a two-dimensional coordinate system rotation. So it will be just a one rotation. So in this case, we can have something like this to understand the relationship between the x1, y1, z1 coordinate system with the x2, y2, z2 coordinate system. So the x2, y2, z2, as you can see, because it's a phi, so the y-axis, y coordinates doesn't change. So the only thing that changes is the x2 and y2, x2 and z2 coordinates, and it's just a phi rotation. So it should be easy to understand. So you have the z1, x1, and rotate it to x2 and z2. Okay. Okay. So and then the final one is the kappa. So let me go back to here. So in this case, you have the first you rotate the phi. Omega. So right now, first of all, x1, y1, z1 is the vertical photo coordinate system, and you can rotate the omega, so it becomes like this, and rotate the phi like this, and finally we will rotate the kappa, so it will be like this. Okay, so from the x2, y2, z2, then finally, if we rotate the kappa, then the final answer will be the x, y, and z. So which is the tilt photo coordinate system, right, which is the tilt photo coordinate system, and in the image space. Okay, so for the kappa rotation is over here. Right, it's over here. So as you can see, because we are rotating along the z-axis, so the z doesn't change. So z equals to z2, and x and y coordinate system will be just like rotation. Okay, so it's like that. Okay, so basically what I'm trying to say is this calculation is from the x1, y1, z1, which is the vertical photo coordinate system. And after you rotate omega, then you have x1, y1, z1. And then you rotate phi, then you have x2, y2, z2. And you rotate kappa, then you have x, y, and z. Okay, that's the case. Okay, should be easy to understand. And then finally, what we can do is, as you can see, this is the relationship between the x, y, z with the x2, y2, and z2. But x2, y2, z2 can be also, well, we can also use the x1, y1, z1, because x2, y2, z2 is also can be represented as x1, y1, z1 coordinate system, and x1, y1, z1 system can be also represented as the x1, y1, z1 coordinate systems. So in this case, we can put everything together, and then eventually we can get something like this. Eventually we can get something like this. So to represent the relationship between the x, y, z with the x1, y1, and z1. So basically that's the case. That's the case. And after you move some terms around, then you have the x equals to x1 multiply something plus the y1 multiply something plus z1 multiply something, and so on and so forth. So this becomes the rotation matrix. This becomes the rotation matrix. So as you can see, we can just call it M11 to M33, and each of the term is over here. And each of them is over here. That's where you can get the rotation matrix. So it's actually very easy. As you can see, it's just three rotations, for the omega, phi, and kappa. And just combine everything together, and voila, you have the rotation matrix. Okay. Okay. Any question? Oh, no question. Then let's talk a little bit more about the rotation matrix. The rotation matrix, the M matrix, that is orthogonal. Orthogonal is called 正交. In Chinese, it's called 正交. So which indicates that this rotation matrix has some spatial characteristics, which means that the inverse of the rotation matrix equals to the transpose of the rotation matrix. So as you can see earlier, what the equation that we get is xyz equals to the rotation matrix multiply the x plot, y plot, and z plot. And in this case, if we want to do, for example, like the from the other way, for example, x plot, y plot, z plot equals to m transpose multiply the x, y, z. Okay, so just like that because it's also orthogonal matrix. Okay, so you can also write it like this. So x plot, y plot, z plot equals to m11 multiply x plus m21 multiply y and m31 multiply z, and so on and so forth, like that. Okay. Okay, any question? No? We're fine, right? Okay, good. So then the next thing that we are going to talk about is how to derive the coordinate condition equation. That is the fun part, I think. In my opinion, in my personal opinion, it's a interesting thing to do, and actually very easy. It's actually not difficult. Okay. Yeah, we should be able to use just the slides to explain that. Okay, so let's do it. All right. So first of all, with that knowledge, with how to derive the relationship between the relationship between the vertical photo coordinate system and the tilt photo coordinate system, and with that in mind, and then here we are going to derive the coordinate condition equation. So this is the variables that we have. So as you can see, we have a tilt photo over here, and then we have the L as the perspective center, and for the image space, we have the x and y, small x and small y coordinates. And then, of course, we have a focal length f over here. And then for the object space, we have the x, y, and z. So these three axes are for the x, y, and z. And XL, YL, and ZL, that indicates the EOP location, the perspective location. Yeah, here is the A point. I think later on we will use the A point as the example. So A point has the XA, YA, and ZA. And if you project this A point to the image, then you appear at here, A point, the small A point. And you have the XA and YA on the photo coordinate system. So those are the variables that we have. So how to derive it? So let's go to the next page. First of all, if you directly start with the tilt photo, then it will be very difficult to try to understand the relationship. So let's simplify the question to become a vertical photo. So assuming that we have a vertical photo taken at exactly the same location, which is L. So as you can see, here is the vertical photo, and earlier, like we introduced over there, the vertical photo is here. So we have the perspective center as the origin, and we have the x plane, y plane, and z plane, which is parallel to the x, y, z coordinate system in the image, in the object space. Okay, so let's assume we are taking a vertical photo. Okay, so in this case, the A point, if you project it to the vertical photo, you have the another A point over here, or you can say A plane point. And this A plane point has the XA plane and YA plane. And so also it has the ZA plane. It also has the ZA plane because the origin is over here, is at the perspective center. So you also have the ZA plane. Right, is this direction, is this distance. So you also have the ZA plane. So with that, and actually we can just use you can say the triangles on this. I don't know. I don't know the full name, the technical term for that. But however, you can use the ratio between the XA plane to the distance in the object space. So you have the XL and XA. So the distance over here, that's this, the distance over here and calculate the ratio between this and also the XA plot over here. So that's this term. That's this term over here. And supposedly this ratio should equals to the YA plot, which is this distance, to the object space distance. So this distance and this distance can also calculate a ratio. And supposedly it will be also equals to the ZA plot, but and also the ratio of ZA plot to the ZL and ZA, which is this distance. So ZL to the ZA, that is this distance, and to the ratio between this one. And so from the origin to your A point Z coordinates, which is ZA plot. So because as you can imagine, as you can notice that here we have a negative sign over here, and the reason for that is because as you can see the Z plot is the positive direction is pointing at the sky. So which means that this A point over here, the ZA plot actually is a negative value. The ZA plot is actually a negative value. But right now the ratio that we want, supposedly we need to have a positive value. So that's why we have the negative sign over here to make this whole term positive. To make this whole term positive, so that it's the same ratio. Okay? This should be easy to understand, right? Okay, so just in case some of you couldn't imagine that, it's basically like this. Let's just say A, B, C, D. Right? So A to B should be equals to C to D. So it should be like that. It just like that. Okay? So I don't know, what's the technical term for that in English? Similar triangulation, similarity, or something like that. No? Yeah, something like that? Maybe. Okay, sure. Anyway, but doesn't matter about what's the like technical term for that. But basically that's the theory. Okay, that's the rule. Okay. So in this case, with this, then we can have this equation. Okay, this equation. Okay. So and after some adjustment, so as you can see, if we only take a look at the x-axis x coordinate ratio with the z coordinate ratio, then we can just rewrite it as xa plot equals to xa minus xl and divided by za minus zl, and then multiply the za plot, something like that. Okay. So also we can write the y plot like this and za plot like this. So that's the case. Okay, this from here to here should be easy, right? Alright, with this, alright, right now, any question? Alright, good. So then all we need to do is eventually we still need to touch the tilt photo. So originally we have the vertical photo, and right now we are going to tilt it to the vertical to the tilt photo coordinate system. So in this case, this is what we have derived earlier. So the rotation matrix to represent the transformation between the x plot, y plot, and z plot, and the x, y, z. Okay. So this is the equation that we have earlier. Okay, should be fine. Right. So in this case, what we are going to do next is eventually what we want is x, y, and z. So we want to replace everything that is x plot, y plot, or z plot. We want to replace everything like that. Everything like that. So in the earlier page here, we have the x plot, y plot, and z plot. So why don't we replace everything over here with what we have over here? Okay, we will just put these to this equation, right? So what we can have is this one. What we can have is this one. So as you can see, the x plot, y plot, z plot has been replaced by that. So and these are the three equations that we have. These are the three equations that we have. So in this case, the XA equals to M11 and multiply this, which originally is the XA plan, and M12 multiply the YA plan, and which is over here, which is written as this over here, and so on and so forth. So we have these three equations. Right now we have these three equations. The next thing that we are going to do is we are going to, because right now we still have the ZA plan demand, right? We still have the ZA plan, so we need to remove the ZA plan. So how to remove the ZA plan? We use the first equation divided by the third equation, and the second equation divided by the third equation. As you can see, let's take a look at the Y and Z. Right, so if we use, let me use this. Okay. Equals to, if you divide this to this, then what you have is ZA plan is gone. All the ZA plan is gone because everything has the ZA plan. So ZA plan is gone, and that also in addition to that, we also remove the ZA minus ZL. We also remove this. Okay. So in this case, whatever remains is M21